Welcome back, guys. Welcome back to another JOCADEMY video. Today we'll be doing an interesting problem. I found this problem over here on YouTube. You know, it was called my all-in-one calculus problem, and I decided I wanted to do it. So this is my first attempt doing this. This is JOCADEMY Sigma Calc ABC. Okay, let's start. So this has integrals, differentiation, series, and integral by parts. So like the big major ones of calc. So now we got limits too. Okay, guys. So where do we even start? Let's start with the bounds. Let's solve the bounds. Okay, so we're writing the bounds. Lim x approaching infinity of ln x square root x. Well, they both, the function of ln x looks something like this, and square root x probably looks the same, not gonna lie. So, and we know that if we increase it to infinity, that both these two functions go to infinity. And one of El Hospital rules is that you can use it when it's in indeterminate form, which is either infinity over infinity or 0 over 0. But there's other forms or ways, but since it goes to infinity, they use El Hospital. So d dx, and then if we do this correctly, we get 2 square root x over x. Now you might be saying, don't we have to use El Hospital again? Well, yes, you could do that, and you'll probably just get 1 over square root x, and that's it. But you don't need to do that. There's a shortcut. Notice that the power, this is to the first power, this is x to the 1/2. Notice how you're approaching infinity of a rational function where the denominator has a higher power than the numerator. When that happens, the asymptote would equal 0, and that means as x approaches infinity, x equals 0. So this equals 0, and this therefore equals 0. And now we can write this as 0. Now we can do the same thing for this one. Do El Hospital again. So it's 1 over 2 square root x over 1 over x, which is equals x over 2 square root x. We can do El Hospital again, and you'd probably just get 1 over square root x, which is equal to square root x. Or you can do the thingy again, like I told you. You didn't have to do that. You could have just got the limit of x approaching infinity of x 2 times square root x. And like I said before, the power. So this is 1/2, this is 1. When the top of a rational function is greater than the numerator, then it goes to infinity when it goes to infinity. So this equals infinity. And also, square root x lim x equals infinity anyway, so. So, now, this type of fraction with infinity is called an improper integral. Remember that integral of f of x dx equals the sigma, the limit of b approaching infinity, b of I, f of x I changing x. Remember this? Well, there's a b to infinity here because you couldn't put infinity here because b replaced it. Now, same thing applies to improper integrals. You cannot have infinity here, so you must have a limit of some variable. It's called b with infinity. Replace it with b. So that's for that. Now onto this d over dx sin squared x squared. That's easy. So we just get the first derivative. We find the square. The u squared equals 2u times u prime. Which one is u prime? Or the inside function? Well, it's this one. So it's gonna be 2 sin x squared times cosine x squared times the inside function again, 2x. So we got 4x sin cosine x squared. There you go. And some of you guys may be thinking that there's an x squared in there. You can't find the integral. Well, just watch me do it. I will. I just don't know until you know. Anyways, 1 plus x squared dot dot dot. What does this mean? Well, this is Maclaurin series. And that is a series that creates a polynomial function. And let's look at the pattern. Let's find a general rule for this pattern. So we got 1 plus x squared plus x to the 4 plus x to 6. And notice that 2 and 6. Notice that. Remember that a Maclaurin series is f of 0 plus f prime of 0 plus f double prime 0 over 2 plus f 0 factorial, right? And then you need x to the 4th. Oh, no, oops, you need x. Don't need x here. You need x here. X squared and x cubed. So this is a general form for Maclaurin series, right? And so this is 1 plus, and then if you notice, this is x squared, and this f prime, so does f prime equal x? Where did that extra x come from, guys? Well, let's notice the pattern of this from the pattern we just got, okay? So, 1, of course, starts x squared. That is fine. And then you realize that x squared is increasing by 2. So, when you're writing a series, or a general rule, you're gonna write this. Or actually, I'll write the n rule. So sigma I n equals 0 to like infinity. And we see that x to the n over n factorial. This will get you 1 plus x squared, whatever. But we notice that the x squared multiplies starting from the first term because this is 0, 1, 2, 3, and so on. So we see that on the first term, it's 2. And on the 0th term, it's 1. And we know 0 factorial equals 1. N to the 0, x to the 0 equals 1. So this works. X to the 2. You can only get that if this was doubled, x to the 2n, and then plus x to the 4th over 2, put in 2, that's x to the 4th over 2 factorial, that's true, 3, you get x to the 6, and 3 factorial is 6, so this is the rule for the thing, but we're not going to put a summation into this box. Why? Because this is actually very close to, like I showed you earlier, this equals e to the x, so that would mean this is equals to e to the 2x, this should equal to e to the x squared, okay? Y'all see that? I hope you can realize that, okay? Alright, so with that, we can replace this with e to the x squared. So let's write this better. This is the final result. And we are not done yet, we have to solve what this equals to. Because this is a definite improper integral. There is a value to be given, so you're equal. And we're first gonna back to gamers, so I spent like an hour doing nothing to redo this. So let's just I forgot stuff. So 4x cosine x squared sine x squared, or something like this. Earlier I was gonna do integral by parts with this. The thing is about integral by parts is that notice that it is only 2 functions, not 4 functions. You see, 1, 2, 3, 4. There's only, you can only use 2, and I had a mistake, and I used 3 functions, and I wasted a whole hour of my life figuring out why I was wrong. So this is where I went wrong. So notice this. Hamburger cheeseburger, Big Mac, hamburger. Okay, so there is a thing where cosine of x, sine of x, multiply each other times 2 equals, actually this equals sine 2x of a half. You don't really need to know why. I think you can find trig identity and easily find out why this is true. But this is this, right? So as long as x and sine and cosine have the same inside, you can do this, and there's a, and yeah, so we're gonna do that. Cosine, sine 2x squared, 2x, just like that. I'm gonna use this over here. So then we only have 1 function, okay? Or there's 3, but I'll show you how to get only 1 function from this. So rewriting this, 2x sine 2x squared dx. All right. So notice that x squared is on the bottom, x squared on the top of the thing, so we can use sub, but also notice that the derivative of x squared equals x, which is just the variable we need to get rid of this. So when we write u equals dx equals 2x over du, and if we plug that in, we get sine 2u over e to the u, or rather e to the negative u dx. b squared u equals b squared u equals 0, then b approaches infinity. The reason why it's b squared is because we have to switch the bounds as we switch variables from the u to x. So you write u to the b equals b squared to the x squared, and u 0 squared. So there. So now we have only 2 functions. 2 functions. And now we can finally use integral by parts. Now let's use LIATs. Log inverse trig algebraic equation and trig exponential function. So notice that there's a trig and exponential function. Trig is before exponential, so that would mean that our u, this is a different u by the way. It's not the same u as this. It's just for notation purposes. Sine 2u du, which is the derivative, equals cosine 2 cosine, oopsies, 2u dv equals negative e, no, it's just e to the negative u dx. b equals negative e to the negative u. So we're gonna write this into this notation. So integral of sine 2u e to negative u d, oh whoops, that should not be a dx, that should be a du equals sine 2u negative e to the negative u minus, or rather plus, because of that negative right there, e to the negative u, oh, and then there's a minus, wait, there's no minus, sorry, that's good, 2 cosine under the du here. Wait, that's embarrassing, du equals, don't worry about the notation like I said. So what we do after here is that we gotta do it again. We gotta do integral by parts. So u again is trig, so it's gonna be now negative 4 sine 2u du. Oops, my bad. This is gonna just be 2 cosine 2u. Oh, there's no space to write. dv equals e to the negative u, of course, and just b again equals negative e to the negative u. Right? Right. Oh wait, du. Okay, so now we gotta rewrite this as, write this entire thing as 2 cosine 2u negative e to the negative u minus, but there's a minus here, but there's also a minus here, v du minus 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 is just minus. So integral e to the negative u times 4, so I'm gonna put down the outside, sine 2u du, and if you notice, this e to the negative u sine 2u du, oh wait, that's embarrassing. Okay. It's the same thing as the original, like right here. This is the original. This is the original. So what we're gonna do is add this to this, and so from there, basically. So let's rewrite, we simplify this, add, we just add here, he gets 5 integral of e to the negative u sine 2u du equal negative sine 2u e negative u minus 2 cosine 2u e to the negative u. Now let's just erase this. Don't need that no more. And then you realize something, guys. You can just factor out e to the negative u, and this is get e to the u, and then this 5 from here, you can divide it, so we got 5 here, erase that. So now we got this equals to negative sine 2u minus 2 cosine 2u over 5 e to the u, right? But remember that we got u equal b squared and u equals 0, and we got a limit as b approaches infinity, right? And remember that integrals of bounds equals f of a minus f of b, right? It doesn't matter if there's a limit there. It's just for the notation. The limit doesn't really affect anything. Okay, kind of does, but... So, what we got now is equal to a limit as b approaches infinity. Oh wait, oops, I wrote that wrong. b over a, okay. Of f of b minus f of a. And all you have to do is just plug in infinity for b, right? And this big F is literally this entire thing. This is the integral. So if you realize that cosine and sine, they can only be either of 2 max or mins. It can be 1 or -1. Those are the only values that sine cosine can ever reach. So that means it's finite. That means it's not going to go anywhere else. But this, on the other hand, e to the infinity equals infinity. And as we learned earlier from the limits that were part of the thing, anything that's bigger over some smaller, like x, is equal to 0. Okay? Especially cosine, because they cannot go even past 1. So that's basically writing e to 5. It's just 0. Okay? So f of b equals 0 already. Or actually, I should not write that. It should equal 0 minus. Now f of a is 0. Yeah, f of a is 0. So if we plug in 0 here, we get 5 e to the 0 is 5. So we can write 5 over negative 2 sine 2u of 0 is 0. And negative 2 cosine. What that is? That is. This is 1 times 2. So that's equal to 2/5. The answer was 2/5 all along. Who would have known? E and